Yeah, let's start. This is the first AMA series that we are doing at STEMnet, where we try to bring experts from academia and industry and help students connect with them, so that they can learn more about the field and try to understand what it is. Many times what happens is we just look at our own syllabus and interact only with our teachers, so we don't really understand the subjects or the details of them in further studies. So for the first AMA that we have Dr. Subhojoy Gupta. He's a professor of mathematics from IISc, and thank you for joining us, Professor Gupta.
Yeah, so let me just say a little bit about what I do. I guess you've already heard. I'm here at the member of the faculty of the math department at IISc, and so my work involves research in mathematics and teaching. So as far as teaching is concerned, I teach all sorts of courses for UG and PG students, as well as I have my own PhD students I need to guide. But my main activity, from my point of view, is mathematics research, where I sort of uncover new mathematical truths. So this is what research is about. It's exciting, and my subject of expertise is geometry and topology. That's what I'm interested in. And so that's some subject and some part of pure mathematics, and it's got a lot of potential applications, and far in the future perhaps. But right now, this is all quite abstract and sort of it involves mathematics, all the mathematics that you learn in college and so on. It's taken all together, sort of algebra analysis and geometry, and so that everything is taken into play in when you do research.
So so I had a question that definitely would help if answered. Just to start with, what is your educational background like? What have you studied in the past, so that people get a context of how you progress towards becoming a professor in mathematics?
So different people have different paths. So I can tell you about mine. So I did my schooling in Kolkata, and after that I went to IIT Kanpur, where I did my 5-year integrated masters in mathematics. So I was always interested in mathematics, even ever since I was a teenager, and so after my undergraduate program, I went to the US, to Yale University. I got a scholarship there to do my PhD. And so after my PhD, I was a postdoctoral researcher, a postdoctoral scholar in Europe and Denmark for a year and a half. Then I was a postdoctoral scholar in Caltech in the US for a year and a half. And after that, I returned to India, as I always wanted to do. And now I'm here at IISc, and I'm continuing with my mathematics research and teaching. So that's been my trajectory.
I see. That's a very interesting, trajectory there. So you always, liked mathematics and you wanted to do something in it, is it?
So this interest started, in my teens, as I said, maybe sort of middle school, and at the time, of course, this was sort of the days of maybe pre-internet or early internet, and so there was no YouTube or something to or things like this, so that one has exposure to mathematics. But it did happen that mathematics was in the news at the time, in newspapers, etc., because there was this major breakthrough in mathematics where this Fermat's last theorem got solved by professor in the US at the time, Andrew Wiles. And it was a big deal because this Fermat's last theorem was a problem that was very simple to state, and it took 400 years or more to solve it. And so this was a sensation at its time, and so this was sort of maybe late 90s, something. So so that sparked my interest. And although I don't do the kind of mathematics that the Fermat's last theorem involves, that was a problem in number theory. So I eventually came to geometry and topology. But nevertheless, I'm sure that had some impression, and so that made me, quite interested in mathematics. And I was lucky to have any encouraging people along the way, and so my sort of friends and teachers, they helped sort of nurture this interest, and yeah, so here I am.
That's absolutely great. One more question that we have is, so in the field of mathematics itself, you focus on a particular area, right? So what are the interesting things in your line of work? Like, what are the exciting things, and what do people think about, and on a broad level?
Yeah, so it's this is a good question, and yes, I'm happy to talk about this because this is what excites me. So it turns out that in mathematics, we were doing mathematics, learning mathematics in school or even college, one would have an impression that these are subjects that are well established, and everything is all set in stone. It was, after all, things like geometry has been around for more than 1,000 years, 2,000 years, if you count Euclid as, beginning Euclidean geometry and so on. But it turns out that, many exciting new developments keep happening. And that's what, math research is all about. And that's true for, all sciences, of course. And so in the late 19th century, people thought that there was no other thing to discover in physics, which is far from being true, right? So it's only in the 20th century that all this, the Einstein's theory of relativity and quantum mechanics and et cetera, they were all born in this and in the 20th century, right? So it's new developments keep happening in the sciences, and it's true of mathematics as well. So I guess in geometry and topology, for example, the fields that I'm broadly in, so this is about, so I study shapes, very roughly speaking, I study shapes. So some shapes are like surfaces, which are two-dimensional surfaces. You can, go in sort of left and right. And so that's like the surface of the Earth. There's latitude and longitude, two parameters that specify where you are on a surface. And that's called a two-dimensional manifold. And there's also, you can also have three-dimensional manifold, like the universe we seem to be living in, right? Which is sort of these three directions where one can go. And so these study of these shapes, the mathematical study of these shapes has been around for a while. Okay, so in the 19th century, Riemann was a German mathematician, and he proposed a way to think about these shapes, and that this is what is now known as Riemannian geometry. And that was used by Einstein, where he gave a very elegant theory of gravity, as as gravity is being a consequence of mass deforming space-time, right? So the shape of the space-time was governed by these equations in Riemannian geometry. And so this mathematics could be put to use. And today we are using Einstein's theory, which needed this mathematics for this formulation. We use it every day because it's part of the calculations involved in GPS. When in the GPS location, your phones will sort of track satellite signals, and they use Einstein's theory of relativity, the general theory of relativity, to account for the fact that Earth's gravity changes the time that the signal needs to reach Earth, and so on. So this is what geometry has led to. And currently, the current developments, for instance, at the turn of this century, the 21st century, around 2003, 2004, there was a big breakthrough where there was a conjecture from a few decades ago. Conjecture in mathematics is an unproved statement which is believed to be true, right? So this is usually proposed by some mathematicians, and then people try to solve it, try to understand why it could be true or why it isn't. So there was a conjecture relating geometry and topology for three-dimensional manifolds, and so I mean, parts of the conjecture were actually more than 100 years old. So people for a century had been, trying to solve this and try to understand, this link between geometry and topology in 3 dimensions. And this around 2003 and 2004, there was a big breakthrough when there was this Russian mathematician who solved that conjecture. Okay, so that was a new development. That was, so landmark development, which takes, some of these things take years and decades and centuries to kind of actually happen. So this was some new thing. There are other new things. For example, one can talk, just as I said, surfaces. One can talk about the space of all surfaces. There's a what mathematicians called Moduli Space. And there was so another recent breakthrough that was even a few years ago. This is part of it was done by Maria Mirzakhani, and she was a famous she was a mathematician. She was a good mathematician. Unfortunately, she passed away at a very young age, about a few years ago. And she won the Fields Medal. She was the first female Fields medalist ever. A Fields Medal is one of the highest honors a mathematician can get. It's one of the awards. There's no Nobel Prize in mathematics, but this is considered to be equal in its prestige. So this Mirzakhani, she worked out, studied these space of all surfaces, this moduli space, and understood, paths and these, how to navigate in these shape in the space of this moduli space. And she had another breakthrough result, which is slightly harder to describe, about this space. So the new things keep happening, and that's what excites me and excites all of us, and mathematics, doing mathematics research. And my hope is to be able to contribute to this ongoing story, which is sort of centuries old now, but and anybody can, once one learns some things and learns to ask the right questions, and so anybody can participate in this ongoing story.
Wow, that is truly inspiring to hear that mathematics is used in very would you say very interesting ways, and from gravity to other things. And I hope that students can appreciate the usefulness of mathematics for every branch of science and technology, because if mathematics wasn't there providing all these different techniques, other sciences cannot make any progress at all. That is something that as we go through school we don't appreciate so much, but then we learn later.